This is my Lab 4 presentation on bar magnets for Physics 2. So the purpose of this lab is to observe the magnetic field measurements of a bar magnet relative to the distance and find the magnetic moment. So fundamental principles that we have here is the magnetic field of a dipole, which is the magnetic field that forms small closed loops from the north and south poles, and it's generated from a magnetic dipole. And the distance dependence formula, which is a formula of the magnetic field in relation to the distance, and the Biot-Savart law, which is the relationship between electric field at a certain location and current. So for the experiment setup, our procedure was to first find the magnetometer chip by marking values where Bx and By are at their maximum value, which is where we marked the X on our phones, and are also orthogonal to the magnetic field, which is how we oriented the horizontal ruler. And then we measure the distance between the bar magnet and the magnetometer for both on and off axis. And as you can see here, I mark the bar magnet in both the on axis and off axis portions and see how we measured each distance value. So the system is the bar magnet with the surroundings being everything else. After we recorded our results stated that n equals around negative 2.1484 with the magnetic dipole equal to around 4.751. So how do we get that calculation? As you can see, we measured the data from the off-axis field and we got a resulting graph. From this resulting graph, we got a linear equation with the slope and y-intercept, and we used this equation to calculate for n. And then we solved for k, and raising e to the 0.7519, we found that k is approximately 2.12. And then we plugged into this equation, simplified with algebra to find that mu equals 4.751. So right here, we just put the value that we just calculated and also drawing the arrows and also coding for the equations that we stated earlier in the presentation. And as you scroll down here, you can see that I declared dperp as 0.2, which makes sense because it is what we set as our dperp value on the off-axis field. And once you generate the program, you can see that the arrows and values are representative of what we described earlier. So looking at the results, only 2 out of the 4 statements are true, with number 1 and number 4 being bolded, which states that the magnetometer, when it's far away from the magnet, it measures a near zero magnetic field in the x direction, and 4, which states that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So we did make some assumptions in this experiment, which is 1, the bar magnet is a dipole, 2, that there are no other external fields acting on the phone, and 3, the magnetic field of a bar magnet decreases with increasing distance. So this causes some potential errors as well, which for number 1, there were other electronic devices during the recording that can also skew the magnetometer recording, and 2, the location of the magnetometer chip was not found correctly due to human error. So a third potential error I want to mention is not completely orienting the horizontal ruler orthogonal to the Earth's magnetic field, which can also introduce some external forces as well. So what if you haven't oriented your experiment to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? So it would be hard to find the relationship between distance and magnetic field of a bar magnet because the magnetic field of the Earth would have an effect on the readings, which is also in the potential errors stated earlier. What if you were to stick 2 identical magnets together, end to end, and run the experiment again? How would you expect your measurements to differ? Well, the magnitude would be much stronger, around maybe 2 times larger, since the magnitude of the magnetic field would increase from the stronger magnetic dipole. And that is the end of the presentation. Thank you for listening.